Hi, my name is Brandon Nelson, and this is my Cap 2 Fate of Lactate. Some major steps of the lactate pathway. So, this diagram illustrates the Cori cycle, which describes how lactate is produced in the skeletal muscle, right here, during exercise and is transported to the liver and converted back to glucose and then returned to the muscle to support continued energy production. So looking at the skeletal muscle, glucose enters the muscle cell from the bloodstream, as we see right here in the diagram, and is converted into glucose 6-phosphate. Through glycolysis, glucose 6-phosphate is then broken down into pyruvate. So it goes through glycolysis, because of glycolysis, glucose 6-phosphate turns into pyruvate, and this process produces the ATP, which fuels the muscle contraction. And during high intensity exercise, ATP demands rise faster than how much the mitochondria can actually keep up with. So now we look at the lactate. When the mitochondrial oxidation is limited, pyruvate is then converted to lactate. This reaction is catalyzed by lactate dehydrogenase. As we can see right here, so the pyruvate is converted to lactate by the lactate dehydrogenase. And it's important to note that NADH right here is converted back to NAD+, because this allows glycolysis to continue producing ATP, which it's a critical step because lactate production does not happen by mistake. It allows glycolysis to continue during very intense exercises for the most part. So now we look at the lactate and how it goes to the liver. So the lactate exits the muscle cell and it travels through the bloodstream, as we see right here in the diagram. And lactate is not trapped in the muscle, it is very mobile. So as the lactate enters the liver, NDH converts the lactate, as we see right here, converts the lactate into pyruvate. And then pyruvate enters the gluconeogenesis. And this process converts the pyruvate, as we see here, into glucose 6-phosphate. And then through gluconeogenesis, it then converts it into glucose. It frees the glucose because then the glucose will go through the bloodstream and go back to the muscle fiber. This step requires energy from the liver, which is why the Cori cycle is considered very metabolically expensive. So now as the glucose 6-phosphate breaks into the glucose will enter the bloodstream and it gets released into circulation, and the glucose returns back to the skeletal muscle, and the cycle can then begin again. So the major takeaway is that the Cori cycle demonstrates that lactate is not a waste product, it is a temporary energy carrier that links the working muscle with the liver to support ongoing movement. As for exercise intensity and training adaptations, this diagram shows how lactate produced during higher intensity exercise is transported and reused, and how training improves this process. So as energy intensity increases, ATP demands rise. Glycolysis speeds up, and especially in fast twitch muscle fibers. So the more pyruvate is converted to lactate to regenerate the NAD+ and sustain the ATP production. So as the lactate right here in the diagram leaves the glycolytic fibers, which is right here, and enters in circulation, this prevents immediate buildup inside the muscle. And the export is facilitated by these MCT transporters. lactate is taken up by the oxidative tissue. So lactate is delivered to the slow twitch muscles, as we see over here, to the brain and the heart, and obviously the muscles. So these tissues have high oxidative capacity. Lactate can be used directly as a fuel source. Now going back to the transporters, the MCT4 helps export the lactate from the glycolytic fibers, and then the MCT1 helps import the lactate into the oxidative fibers through here. Endurance training increases the MCT1 expression. So once inside these oxidative cells, lactate is converted back to pyruvate, and it enters the mitochondria and the TCA cycle. So training intensity, mitochondrial density, and oxidative enzymes. So the major takeaway is that higher intensity increases lactate production, and training improves lactate transport and oxidation. So lactate versus lactic acid. So this diagram explains why lactic acid buildup is a very misleading term, and it clarifies the difference between lactate and lactic acid in the body. So during glycolysis, glucose or glycogen is broken down with pyruvate. When ATP demand is high, pyruvate is converted into lactate through lactic fermentation, as we see right here in the diagram. This reaction allows glycolysis to continue by regenerating the NAD+. So right here we have the lactate leaving the muscle right here. Although the term lactic acid is very commonly used, lactic acid does not remain intact in the muscle, as we see here. It immediately dissociates into lactate and hydrogen ions, or H+, as we see here. So lactate is a stable molecule that can be transported in the blood, as we see it go through the bloodstream. And hydrogen ions accumulate separately and are responsible for lowering the pH. The drop in pH is what contributes to the burning sensation that you feel during a higher intensity exercise. So now the role of the liver. So lactate is then taken up by the liver, and it can be converted back into glucose through gluconeogenesis, as we see here in the diagram. So through gluconeogenesis, the lactate is taken up and turns into glucose. And then the glucose can be stored as glycogen, as we see here, or it can be returned back into circulation. Lactate itself is not harmful. It serves as a transportable energy. The lactate formation actually helps delay fatigue by allowing ATP production to continue. So the takeaway from this is that lactic acid does not accumulate in the muscle during exercise. Lactate accumulates and can be reused metabolically. And hydrogen ions are responsible for that acidosis and fatigue related effects. Then we move on. So this diagram shows how lactate can be used as a metabolic fuel by multiple tissues, and how rising lactate reflects increasing metabolic stress during exercises. So as exercise intensity increases, glycolysis accelerates in the muscle. So pyruvate is converted to lactate to regenerate the NAD+, allowing ATP production to continue. Lactate accumulates inside the muscle cell alongside hydrogen ions, as we see right here. So the lactate is regenerated by the NAD+. The pyruvate is converted to lactate to regenerate the NAD+, allowing the ATP production to continue. Lactate accumulates inside the muscle alongside these hydrogen ions right here. Lactate is transported then out of the muscle cell by these MCT transporters. This prevents the intercellular buildup and allows lactate to then enter the circulation, as we see right here, as it can be sent off. So lactate travels through the bloodstream, as we see here in the diagram, and can be taken up by the heart, which uses the lactate as fuel to fuel the oxidative muscle fibers, which can oxidize the lactate in the mitochondria. The brain, right here, especially during prolonged exercise, and the liver, right here, where lactate can contribute to glucose production. So then once inside the oxidative cells, lactate is converted back to pyruvate, and the pyruvate enters the mitochondria and feeds into the TCA cycle. This allows lactate to then directly contribute to ATP production. So high blood lactate indicates a high rate of glycolysis. And then as lactate rises, there's a more reliance on the carbohydrate metabolism as that increases. So fatty acid oxidation becomes then down regulated as exercise intensity rises.